Okay, so let's look at the standard model with three fundamental particles now that they've grouped things into. So you've got the quarks, leptons, and the bosons. So we start with the bosons here. This is a new idea that actually sort of gives us a particle that's responsible for force. So this exchange particle mediates the force between particles and actually is responsible for the four key forces we've actually done before. So first of all, you've got electromagnetic. Now the boson for that, or the gauge boson for that in this case, is actually the photon, the virtual photon. And what happens here is if you get two charged particles approaching each other, or near each other, say two electrons, there'll be a photon exchange that goes on there between the two particles in both directions, and that photon is actually what exerts a force on each other, on the two particles. So one particle exerts a force on the other one by a photon exchange and vice versa. Okay? Now if you can picture sort of two people with ice skates there on ice, when one person throws a ball to the other one, that second person then will actually be forced backwards by that, and that's a repulsion force. And if the other person throws a basketball this way, the same sort of thing would happen. So the two will be pushed apart by these photons exchanging like that, if you like, going like this, in the two directions. Okay? And the belief is that when you're closer, the photons actually happen more often, or more energy is transferred by those photons, so the force is bigger. And because photons have got no mass, that occurs over a very long range very effectively. Okay? Now, in terms of why would opposites attract then, I've seen an analogy for this that sort of helps explain it. And that analogy is that if you throw a boomerang there, this one throwing a boomerang like that, okay, as it comes back it would push the negative particle towards the other one, and vice versa. So think of a boomerang photon doing the same sort of thing there. Alright, and then you get traction. So this is the idea of a gauge boson here. One of them is for electromagnetic force, and this is the one, this photon exchange is responsible for electromagnetic force over a distance. So that's that one. The other gauge bosons here, depending on the other forces, are. Now the other force to consider is the strong nuclear force. So we've already looked at the atom in terms of having protons and neutrons inside its nucleus like this. And we're aware that some of those nuclei have really large number of protons inside. So you've got a photon exchange going on causing repulsion between the positively charged particles, and this is this electromagnetic force with the photon gauge boson. So there must be quite a strong force holding this together so the nucleus doesn't fly apart. So when you look at that one, it's a strong nuclear force that acts between those, and this only acts on things called quarks, by the way, which we'll come into later, and these are definitely composed of quarks. But the strong nuclear force is actually gluing these together, these nucleons, if you like. So that particular one is done by a thing called gluons. Okay? So whereas photons are responsible for electromagnetic there, the strong nuclear force is being responsible by the gluons there. And the same sort of photon exchange, the same gluon exchange is occurring there, or gauge boson exchange. So that's that one. There's another one called a weak nuclear force you can use. Weak nuclear. And this is involved in a few things, but certainly with radioactive decay. So when we've done last year, we looked at the fact that a proton could be converted into a neutron, and when it did that, to conserve charge, the nucleon number had to be the same, so that's all right. But to conserve the positive charge, what would be released is a thing called a positron in this case. And that positron would be accompanied by a neutrino, which doesn't have a mass number or a charge either. And we looked at that last year, and that was our first discussion about antimatter, and they use them in PET scanners. So, the gauge boson for this decay process here, which involves the weak nuclear force, will be a W plus particle, W minus, or there's also a Z one there. All right? And just bear in mind that some of the interactions with leptons are involving with these as well. So there's your third one. The weak nuclear force is your third type of force, and it's your W or Z bosons that come into play there. The last one there is a gravitational force, and the gauge boson for that is going to be the graviton. But we don't study much on that this year. Okay? So there's your four types of forces, and there's your four types of gauge bosons. So think of that as being a separate thing. This is what your gauge boson particles are doing here, causing the force going on. The thing in terms of matter then is you've either got quarks here or you've got leptons. So let's start to look at some of these particles that make up all matter here. So the quarks, you'd actually be very familiar with the up quark and the down quark. Okay? So the up quark and the down quark is what's responsible for the protons and the neutrons that are inside our atoms. So if you think of the up one as having a charge of plus 2/3 of an electron there, okay, and the down one is having a charge of minus 1/3 of an electron, if you've got protons inside your nucleus then, they're actually made of 2 up quarks and a down quark. So you've actually got 3 quark particles in there forming your proton that you're familiar with. Okay? And if you check the charge on that, what you've got is you've got plus 2/3, because you've got an up quark of an electron. You've got another plus 2/3, and then minus 1/3. So that's plus 4/3, minus 1/3, you've got plus 3/3 of an electron. In other words, you've got plus 1 electron charge there. So the equivalent electron, but a positive version. So that's what the proton's made of. Okay, these 3 quarks there. And it's important to realise that quarks can't exist on their own. They're different to leptons, which we'll come to later. Quarks like to go in pairs or threes, okay, to make sure the charges are whole numbers like 0 or plus 1, for example. Okay, so you've actually got 2 familiar ones there that you should know about for protons and also the neutron part of it. If you look at a neutron then, that's actually 2 downs and an up you'll find inside the neutron, or forming the neutron. And you've got minus 1/3 is minus 2/3, plus 2/3 you get a neutral charge there. So that's your neutron. So just try and keep in mind, this is what the up quark is, this is what the down quark is, and the others are going to be similar. So there are other types of quarks to be aware of here. So you've got your charm and your strange, all right, which actually you've got plus 2/3 electron and minus 1/3. So in terms of charge, these are the same. And you then got your top and your bottom quarks as well. So if you think of these actually behaving the same as each other in terms of the amount of charge they've got there, up, down, charm, strange, and top and bottom, if you understand that one, the rest of these are pretty much just bigger or more energetic versions, if you like, of those. So you can think of those as a larger mass or a larger energy. So these quarks here are just heavier versions of this first one that we're actually familiar with. And this is the one that pretty much all matter is made of that we're aware of, okay? You've got your protons and neutrons forming most atoms, and this is what it's coming from, the up quark and the down quark, okay? So if you start to look at the table here, what I've got here is, I've made some notes here for you. You've got your gauge bosons, your force carriers, which are there, okay? Is here. You've got your virtual photon there, which is electromagnetic, your gluon, boson, and so on. There's 2 types there that have been grouped. You've also got your quarks, which are up and down here. You've got your charmed and your strange, and again top and bottom. So just think of these as actually getting heavier as you go from first generation to second and into third. Okay, so there's your quarks. So don't forget they need to exist in pairs or in threes. All right. So as pairs, they're actually called baryons. Okay, and as threes, they're called mesons, which we'll come to that later on. Now, leptons, then, these live on their own kind of thing because they've already got the correct charge, I guess, if you think of it that way. They've got exactly 1 electron minus 1 electron charge. So electrons are what we're most familiar with. So if you think of matter as being made up of these 3 things, that's our typical version of matter we've had so far. All right. But as I said before, when you've got a decay process going on, electrons are often released and then a neutrino would come with it, or in some cases an antineutrino comes off an electron. Okay, so this is an electron neutrino that's coming off with a charge of 0. This is an electron. That's a lepton. That's a lepton. And the heavier versions of this electron and electron neutrino would be the muon and muon neutrino, and then finally the tau and the tau neutrino. Okay, so just bear that in mind. But again, these are all thought of as being more energetic as you go to your right there. So try and focus on this first column with your understanding, and then you can transfer that into the second one and the third one. They're just different versions of that. So if we look at some of these here, we've actually said that the quarks can exist in groups of 3, known as a baryon, forming, for example, a neutron or a proton. We've said that. So you end up with a +1 or a 0 or a -1, you'll find. That's based on antimatter, in other words. They can exist in also groups of 2, known as a meson, and you'll find these examples of those called pions, and the whole range of those we'll cover later on. All right. So I've just put some examples in that table there of baryons and some examples there of mesons there. All right, which is a quark and an antiquark combined. So something to bear in mind is that all these particles we've looked at so far on this side for matter here, these all have their own anti-particles there. So there's an anti-up, there's an anti-down, anti-charmed, anti-strange, and so on. And these will be the same except for the fact that their charge will be reversed, all right, and their baryon number. So just bear that in mind. So the baryon number here will be reversed as well, but we haven't done baryon numbers just yet. But just think of their charges as being the opposite. And of course, for neutrinos, they haven't got a charge, so you haven't got an issue there at the moment for that. So what we're saying here is that for every elementary matter particle that's up there, the quarks and the leptons, you've got an antiparticle, and that's equivalent to that, okay? So just bear that in mind. So for the anti-charm quark, for example, they show that with a C with a bar above it. You're actually talking about the same as the charm quark, except the charge is the opposite. It's not plus 2/3 E, like it is for the charm one, it's minus 2/3 E, okay? Now don't forget then that the quarks then are existing in groups there, and they come in fractions of charge for electrical charge. When you look at the electrons, key things here is that they exist as solitary particles, okay? So electrons, and then you've got muons, and then you've got tau particles. They've got a charge of a whole number there, minus 1e in this case here. The antiparticles, by the way, the anti-electron, would have a charge of plus 1e. The anti-muon, plus 1e. The anti-tau, plus 1e. All right? So they do not have to combine together. Okay? Neutrinos often form during a nuclear decay when the electrons and the muons and taus are involved. So just bear that in mind. I've already put some notes here about the composite particles for quarks there. All right? And you've got your baryons, and you've also got your mesons there. Okay? Now, let's start to look at conservation laws.